very excited to be here today with the, I think, first ever serverless community day, and like also very excited about speaking in front of the APAC region community for the first time. So today I'm going to talk about how actually we can take advantage of chaos engineering in serverless environments, how we can break the server things on purpose. And I believe that everyone has this happiest memory that like they were sitting in the office, everything was very smooth. They were thinking about the after time activities. And they are sure that there won't be any problem with their system because they did enough level of unit test, enough level of integration test, and enough level of user acceptance test. Like everything seems very how can I say, normal and beautiful and wonderful. But if you are dealing with distributed systems, as the AWS CTO Dr. Werner Vogel say, everything fails, and everything fails at any time. And for this reason, your team can face a problem, even if that like it seems very normal with all the tests that you conduct, and every you know precaution that you take, but like there are still problems that are not directly related with you but can take your system down. So for this reason, you need to have actually chaos engineering in place. You need to start experimenting chaos engineering, if you still didn't. And when they ask me like what is chaos engineering, actually it's the very short answer is like it's about like asking one question, and this question is what if. So you need to be very suspicious about your system, and you need to constantly ask that question, what if. So you can say that, what if my third party API starts responding so slowly, so and your database becomes unreachable. For example, like I don't think that this would happen again, but what happens if the whole region of availability zones or whatever goes down? And you can also ask yourself that, what if my downstream lambda times out? Like what if your part of your systems becomes not usable, and you are depending on that part? So chaos engineering is about this question. You need to run experiments to answer such questions. And when it comes to serverless, uh, chaos engineering becomes much more, how can I say, inherited already, because uh, everything is now a lot more granular. So for a single microservice that does like several jobs, you have now maybe five, maybe 10, maybe even less, maybe even more functions, and that makes everything much more granular. And for this reason, now the failure, or if you look at from that perspective, attack surface expanding, and there are like new failure types like timeouts, like out of memory exceptions, because like now we have with serverless we have limited resources, so you cannot use the uh, more than 3 GB of memory, or you cannot have more than 15 minutes of time for your application. Just because of those, chaos engineering and serverless is kind of a you know very perfect match, not in a good way maybe, but also like you need to experiment chaos experiments. You need to see what will happen in your systems when something goes wrong, in server systems even more than the other distributed systems. So before jumping into the topic, I'd like to introduce myself. I'm Emrah Samdan, and I'm the VP of product for Tundra, and which is an observability tool on serverless and also for containers. And we also have some chaos, like by the tool, not in the tool. And before jumping to a product management role, I was a developer for more than 6 years, and I'm now a product manager for almost 3 years. And I'm kind of a very enthusiastic about serverless movement. I'm the co-organizing committee for Serverless Days Istanbul here, and also we are organizing Serverless Days Virtual, and we are planning to bring it to APAC region for the next event, and it will be end of July. So stay tuned for the news, and just like you can reach out me over Twitter, and just talk about like serverless, chaos engineering, observability, security, whatever you want, or even like normal stuff, and I will be very happy to socialize with you guys. So Today I'm going to first talk about what's not chaos engineering, because like there are some misunderstandings in this, and then we will talk about what do we need to have in order to actually start doing chaos experiments. And then I will just like talk about how we simply do this. I will mention about why chaos is more important in serverless. I will make a very quick demo showing you like a very small chaos experiment in serverless. So let's start with this. So people think that like chaos engineering is kind of a funny activity that we are doing just to uh, cause a damage, but like apparently it is not. It's about like simulating some of the issues in a kind of a controlled environment, and just detecting the outcomes, like negative outcomes of these issues, and fixing these issues before they cause a real outage in our system. So as I say, chaos engineering is not about just breaking down the system for no reason. It's just like injecting a controlled failure to see if it breaks, and if it breaks, halt it, and just like find a fix, deploy it, and make your system more resilient. And it's not about just, hey, this is the chaos day, I'm now starting the chaos. And it's not about surprising your colleagues. So, like chaos experiments, or in other words, like game days, they call it as well, should be planned ahead. And like everyone in the company, everyone in the organization should be aware of that. It's not about just developers or, the department that does the chaos experiment, because like you may not know that like what will be the effect of chaos experiments. So that's why you need to inform the customer success. Like if your chaos experiment goes very bad, there might be some problems that really your customers can face if you are doing it on production, of course. And you need to inform the other departments. You need to inform the SREs, DevOps people, and this should be planned and communicated ahead. So also, it's not about to blame other people. Like when you conduct a chaos experiment, and if you are lucky, when you face a problem before you actually face it on production, uh, this problem will have a cause, right? And when you just reveal this cause, it's not about to blame others. It's about just to improve each other. So it's not about, hey, your module became obsolete when we inject this failure. Your module became problematic, and it's not about this. We are just trying to improve our product, and also at the same time improve our communication skills when this situation really happens. It actually tests not only the system but also the people. And this is kind of a kind of underestimated, underrated uh, side of the chaos engineering. Chaos engineering is about like defining the steady state. It's like this is kind of the first step of chaos engineering experiments, but this is somehow the most important one in my opinion, because in order to make a chaos engineering experiment, you need to first know that what is normal for your system, what's the up and downs, and for this reason you are actually defining by checking the historical data, by checking using the observable tool in place. You are defining what is expected for your system. You know that, like, hey, my system can take that much of traffic on Friday nights, and the latency goes up to, I don't know, let's say 500 milliseconds for some service, and but normally it is like 100 milliseconds. This is like kind of gold, because you know that like how far it could go. And in this way, like you may know that like when you inject a failure, you may know that what you should expect and what you should classify as failure on for the overall system. And it's like actually we are much more into this in these days. It's like injecting a vaccine to your system. You all need that vaccine in these days. And it's like when you inject a failure to your system, actually you are just like putting a controlled experiment, controlled failure, and you see how your system will react. And it's about like making your system immune to that failure when it really happens in the production. So it's just like injecting vaccine to your body. And it is about like achieving confidence and resilience. So you will now be more sure about like what will happen when the real turbulent conditions happen, and how your system will react. It will react resiliently, or it will just collapse. You will actually achieve this confidence on your system. And I really like that quote from Game of Thrones, the TV series. And it was like the context was completely different, as you can imagine, but this just perfectly fits into like the context of chaos engineering as well. As Littlefinger says, chaos isn't a pit for you; it's just a ladder, just an opportunity to improve your system and yourself. And like, let's talk about this. So like, I think that like I am just talking with many people about this. So people think that, hey, we are just small organization, we don't have time for chaos experiments. But the thing is, like your system still runs on distributed architecture, and the failures that are not because of you, or maybe because of you, uh, is increasing day by day. So you don't need to be a kind of a Netflix or like a big some other big company, Expedia, to run chaos experiments, or like you can just start doing some chaos experiments, and your chaos experiments doesn't have to be like as complex as theirs, doesn't have to be on the production for the first time. This is actually very important. So you may think that, hey, it's better not to play with the production, and I completely agree. You don't need to start with injecting chaos to production environment. You can start with the staging environment, even with your development environment, and just test some of the hypotheses. I will come up in a minute. So and and you don't need to start like injecting chaos to whole your system. You can start with a very small blast radius, and you can start with the like the some very sub modules of your system, and see how the other part of system reacts. After that, you can actually increase the blast radius and see what will happen. So as I say, like you don't need to be Netflix, you don't need to be do it on production, but you need to start, because the distributed systems require this, and you can start small and grow stronger. This is kind of the main flow of a chaos experiment. So the first thing is that knowing about steady state. The second is coming up with an hypothesis, and the third and the real thing is just running the experiment. And after that, you either actually see that the experiment you will run will actually cause a problem in your system, and this is kind of an opportunity to halt the experiment and fix the problem, or your system will not fail, but you will again measure and learn the some other up and downs. Maybe you will change the definition of steady state for you. So this, like, in any cases, you are learning something. So let's talk about what is steady state. So I just mentioned about this just now, but like it's about just understanding what is expected. I'm not saying normal, what is expected for your system. And you can see what is the maximum percentile of duration, 99 percentile, 90 percentile of duration. What's the number of, let's say, time matters that you can take in a limited time. And for all of that, you should have an observable tool in place. So you cannot just, and you should not actually just start implementing chaos experiments without without like a without you without having a way of measuring what will happen. So you need to have a monitoring tool, or better, like an observability tool which uses the attributes of observability, and you need to actually know what is normal for your system. And you need to check the system level metrics like memory usage, latency, CPU usage. Also, you can also check what's the business level metrics, which is normal for me. So what's my aptX score for my application, if it's talking with people, of course. What's the number of transactions in a limited time? What's the throughput in your system, and so on and so forth. So you need to actually have a kind of an understanding of what is normal, what is expected. Sorry, not normal. What's expected for your system. Then you need to come up with an hypothesis. So this is about this asking that question, this what if question. So you can ask that, what if I inject the latency on my system to every lambda in my application, and and how the rest of the system will react. You need to ask like, what if my DynamoDB table becomes unreachable? And your claim would be my responses will still be in an acceptable latency range when there is like bigger latencies in my Lambda functions. My system will continue performing graceful service degradation, and so on and so forth. So then you will run the experiment. So in order to run the experiment, you need to start with a small blast radius. So when I say blast radius, I'm just talking about really the blast. What will blast in your system. You will inject a failure to your system, but will you inject the failure to every other Lambda function, or inject the failure into one Lambda function or one database? And the wise choice is just starting with a small blast radius. Even in the same experiment, you can just run some sub experiments. One is with a small blast radius, the other one is a bit like bigger, and another one is a bit like another a bit more bigger, and it goes up this. But the thing is that you need to actually be in charge of what you are doing. And the second and very important thing is that you need to have a stop button somewhere. You need to just know how to like stop the experiment, how to roll back, and you need to understand if something goes terribly wrong. You need to have a way of just taking it back before instead of just responding to it. You may select to actually halt it and have a rollback plan. And you need to plan the day ahead. So it's not about just, hey, let's make a chaos experiment. It's not working in this way. You need to plan the day ahead of like maybe 1 week, maybe 1 month, not to surprise others, like just to let people to communicate between departments. And in this way, you can actually run a successful chaos experiment. And as I said, you don't need to start in production for the first time. So the others, like let's say you run the experiment and there's nothing wrong. So your hypothesis is true, but you still learn lots of stuff as a team, not as an individual. Like how you are going to get alerted, how you are going to see the impact in the system, not only in the node or the application or the resource when the failure happens. You will see the impact on all the system, and you will see how to respond as a team. It's not about how to respond as an individual, how to respond as a team, how you are going to actually escalate this issue to others, how you are going to notify your users, how you are going to arrange the graceful degradation. And in this way, you will learn a lot about this. So let's say it is actually broken. And this is kind of an opportunity for you because now you have the time and the flexibility to fix the errors. And it's not about just, you see the problem, hey, what caused that? It's like, why, like, we need to find the, like, responsible people, and we need to uh, just like talk about this is not acceptable, this is acceptable. So chaos experiments is about finding turbulent conditions which you may not think yourself, which you may not think as a team. It's about just try something and reveal some unknowns. So the issues that most probably you write a test about it, most probably you took your precautions. But chaos experiments is all about like just testing for unknowns. So you don't know what will happen when you inject the latency to your lambda function, which is like for more like, let's say, 10 minutes if you have enough timeout. So you can just try this on the system. And it's not about just like putting, hey, if the if this team's module becomes resilient as an experiment, they will just gain a bonus. This is kind of a very wrong way of doing this. You don't need to. You don't not. It's not about need to. You shouldn't actually put performance targets for the people about the results of experiments. So let's talk about serverless chaos experiments. And these serverless chaos experiments, there are many things that you could do. So you can just like inject some failures to your Lambda functions, or interactions with AWS or non-AWS services. And you can inject latencies to, to Lambda functions or to the interactions with other resources. You can change the concurrency settings of Lambda functions. So like what happens when you limit the concurrency with 5 and like when your system gets to more traffic. You can see what happens when the IAM permissions are configured not very properly, and which is very common actually. And you can just ask that question: what if the unreachable third-party API or downstream service, which might be Lambda or not, becomes unreachable? And there are many other examples about it. So I don't want to just continue talking, and I'd like to give a demo about like how you can actually run a chaos experiment using Tandra's chaos experiment thing. So in this view, I have this very small lambda function, which actually does something, something not, something very trivial. It's asking for a user from cache, and after that, if it cannot find the user in the cache, it just asks the same question to Dynamo. After if the function could find the user, it's just like it is just setting the user to cache again. It's about just like getting a user from somewhere. And this function normally will behave like, let's increase the, oops, once again. This function will normally does this in this way. So it will just, this is from a Thunder console. It will just ask to Redis, hey, give me the user with the ID of 19. I couldn't. Here, let's get it from, Dynamo, and after that, let's set it to Redis again. So, like very simple, very straightforward thing. And the thing is, so you need to ask, what if Redis becomes unreachable? And you can just ask this question using Tundra. So you can just see that, hey, this is how we are doing in Tundra about this. You can say that this is our span filter. I like to filter the spans whose class name is Redis, which means that I like to just filter the operations that goes to Redis. And I like to inject this error, connection error, Redis connection error, to each and every span. So this is not a good blast radius, but you are just keeping the blast radius small by limiting the experiment with one lambda function. And then after that, you are just matching the error and the filter together, and you are just registering into Thunder. In this way, we will now see that like we will face a problem in our Redis application. So let's save this. And is it saved? Yeah. Then test it. Then it failed. We can check the invocations here. It got the connection error, and the thing is, now your lambda is also failing. So since you actually didn't do anything about these Redis connection errors, like one part of your lambda becomes problematic. You see this problem in your lambda application as well. And this was the request, and this was the the error message and error kind and everything. So this is not something that we could want to. So what you could do instead is just like something very, very trivial. Just like put the Redis connection in try catch mechanism, and in this way you can just, oops, you can just like make your system more resilient. You say user is on, and right, and we need to also put this to here. Anyway, we need to then just test this. There was no problem. And you can then just go check in Tundra if this is possible. So we still see in this application, Redis is still problematic. Redis is still down, but somehow your application just get the user from Dynamo with no problem, as if the Redis cannot give the user. So and your function is performing normally. This is not about like now you saw that it's about just you fixed an issue with a kind of a circuit breaker kind of approach by just putting the connections to try and catch. And in this way, you can also see the logs. Like logs are disabled in my account, so you can also see what happened here, and in this way, you make your system more resilient. So this is like a very simple but yet very powerful experiment. So turn back to presentation just to give the last notes. So what is the common fixes? You can just use exponential backoff mechanisms for your APIs. You can put the circuit breakers. And if we could talk about the timeouts for synchronous communication. So let's say that a lambda function is calling another lambda function and it is calling it like synchronously. This is not the best way of doing this, but let's say you are doing this. And if the function which is to be called has the timeout of, let's say, 5 seconds, and the function which is calling it has the function of timeout of 4 seconds, let's say, which means that like when the inner function performs normally in 4.5 seconds, the outer function will time out. So when tuning your timeouts, you need to be careful about this as well. And just for this reason, maybe for some many other reasons, you need to use async communication when possible. So let's talk about the key takeaways of this day. So chaos engineering is about like making your system ready for the real turbulent conditions in production. And so since serverless is highly distributed and asynchronous, chaos is already inherited. So you need to better get used to it. You need to run chaos experiments and just understand what would happen, what can be broken. And we are running these experiments to improve our system and to improve our skills, both our technical skills and also communication skills, also like a skills to behave as a team. And this is very important. And we need to just like not be very satisfied with the chaos experiments and make it habitual. So also we need to also just be very nice to people that we are working with and hack the ops. Thanks a lot for your time, and thank you for listening my presentation. You can follow me on Twitter